Okay, so we just see a way to multiply a matrix and a vector. And I guess you kind of can tell what I'm trying to say. I'm going to tell you that actually matrix and vector, you can do the same multiplication, but give a different point of view. And this time, we are going to look at that by rows. So let A be a matrix, but this matrix, we only know what are the rows. Okay, so let's see. Okay, to make it more precise, here is the transpose. Okay, so if we do a vector, usually it is a column vector, but if you make it a flat one, then we do the transpose. And ignore that one if you don't care about it. Okay, so suppose we know the rows of the matrix, and I have a vector V. And V is of the same length of this vector, and it is in Rn. Rn. Okay, so you know that the length of this, suppose A is m by n. Okay, then I have another vector of the same length as the R1, R2, and Rn. Okay, so this is also a very easy observation. The vector A times V is equal to another vector, right? And this vector is equal to R1 inner product with V and Rm inner product with V. Okay, so you know this, I believe so. Yeah, it's actually the definition of the multiplication. And so what I wanted to point out is such a thing, this inner product equal to something has a nice structure. It's called a hyperplane. So it's basically a plane, but it's a higher dimensional plane, so we call it hyperplane. Okay, so for example, let's look at this one. This one, suppose I have a plane, and it is the plane defined by this 1, 1, 1. And 1, 1, 1 is its normal vector, 法向量. Okay, so this vector is orthogonal to each vector on the plane. And you know this plane has a different name. We usually write it as all the x, y, z, such that x plus y plus z is equal to 0. But you can see that this xyz, probably your high school teacher told you that this 1, 1, 1 is the coefficient of this linear equation. And the reason is this xyz is equal to the inner product of 1, 1, 1 and xyz. Right? So this equation tells you that xyz is a vector whose inner product with 1, 1, 1 is equal to 0. So this thing tells you that I'm collecting all the vectors that is orthogonal to 1, 1, 1. And some other example is like this. It's a plane that also has a normal vector as 1, 1, 1, but it is away from the origin. Here is the origin, but your plane is a bit far from the origin. And you know this plan can be written as something like this. For example, x plus y plus z equal to 10. Just an example, okay? But the point is, there is some number here instead of 0. If it is 0, it will pass through the origin. But this number, let me call that as b, is just a number. It can determine how far this plane is away from the origin. Oh, sorry, I keep using the red one. Okay, I will switch to the blue later. So anyway, something like this, we call that as a plane. But in higher dimensional space, we might not have a structure like this. We need a higher dimensional plane, which we call that as the hyperplane. So here is the definition. A hyperplane is a set of vectors of the form it collects all the vectors such that R, a normal vector, inner product with this V is equal to certain B. For some vector R and B as the real number. So usually this R is called the normal vector. Normal has different meanings, like 正常的, right? But normal also has a meaning means 正规的. So it's kind of the standard one, the standard vector for this this plane. We call that 法向量. And the B is called the bias. It's just a name, okay? It tells you how far it is from the origin. 偏差量. So such a plane has a nice structure. It happens in any dimension now. Previously, you only have a three-dimensional. In the three-dimensional space, you have a real plane, the plane that we understand. It is two-dimensional. And in the R2, in the two-dimensional space, let me use this. In a two-dimensional space, then you can draw a straight line. This straight line also has a normal vector R, and you can determine what is B here. I keep saying controlled by B because this number is not B, okay? But if B is bigger, then this line will push forward. If B is equal to 0, it will pass through the origin. If B is a minus number, then it will be on this side. Okay, so hyperplane is basically in a two-dimensional space is a straight line. Hyperplane in three-dimensional space is a plane. Hyperplane for n-dimensional space is n-1 subspaces. Okay, just giving you some more intuition about this. So I will, as I mentioned, I want to give you some application. Now you see, as long as you give me a vector and give me a value b, then I'm able to define a hyperplane. And the nice thing about the hyperplane is such an hyperplane partitioned the space into 3 parts. What do I mean? If I have a space, and such a space has a vector, normal vector R, and it has a bias, that's called a B, then you can say there are 3 cases. The first case is the hyperplane itself. I call that H0. This H0 is defined by all the V such that, let me move everything to the left. Such that the inner product of V and R is equal to 0. Okay, but then there is another space. By space, I mean a region, an area such that it collects all the vector where V inner product with R is positive. On the other side, you got another region where the inner product of V and V and R is a negative number. And you can use this to determine, okay, where are you? I'm in the positive region, I'm at the boundary, I'm at the negative region. So this one helps us to determine like where are we in a space. And it is very useful in, say, machine learning that you want to partition 2 sets. So here is what I meant. Sorry, I'm a bit fast here, but I will put the slide on the Cyber University. Okay, here is an application. You see lots of application like image recognition. Like when you go to the parking lot, nowadays you don't go to a kiosk to pay and talk to people. You just stay there and they will take an image of your plate and understand what is the number. So the thing is, every photo or image, say I have a photo of a cat, then you can partition that. If this photo is P by Q, then you can make it into a very long vector, P times Q. Okay, so you can put it in a higher dimensional space, RPQ. So every image, you know, each pixel is just a number, 0 to 255. And these numbers, if you read it from the left to right, left to right, left to right, okay, forget about it. Anyway, it can be treated as a vector. Then, as long as you collect a lot of images, then it looks like this in a higher dimensional space. Okay, then you collect 100 photos, and you put these photos on the higher dimensional space. Although we cannot read it, but computer can deal with that. And probably there are some good tendencies such that maybe these are the photos of a dog. And probably here is the photos of the cats. So suppose we can find a hyperplane defined by normal vector and a bias B. Suppose we can find that such that it cut it into two spaces. Okay? If we found something like this, it's just a vector and a number. And everything that is a photo of a dog is on the right-hand side, and every photo of the cats belong to the left-hand side. This is H plus, this is H minus. So in the future, you can make a prediction. If you have a new photo, and suppose it is in H plus, then you can make a prediction saying, okay, I think this new photo is more close to a dog. And on the other side, you can guess that if it is in the region of H minus, then it is a cat. Okay, so it is something like this that help us to understand the behavior of several points in the higher dimensional space. And indeed, this technique is quite useful, and it has a good accuracy, 准确率, for basic data. And that's also how I do the image recognition for the handwritten digits, 0 to 9, the photos of your quiz. And this part, is called machine learning.